In this example, we will use Newton's law of cooling to solve this problem. First of all, it says that a thermometer is reading 10 degrees Celsius is brought into a room with a constant temperature of 28 degrees Celsius. Wouldn't it make sense that then this temperature is going to increase until it reaches 28 degrees? And it will level off eventually at 28 degrees. It will not continuously increase past the 28 degrees. If the thermometer reads 16 degrees Celsius after 2 minutes, what will it read after being in the room for 4 minutes and for 9 minutes? So those two questions themselves would be very easy if we just had a model. And this is where Newton's law of cooling comes in. And it's stated here, and I've just screenshot this from the e-text on page 362. So Newton's law of cooling states that the temperature of a heated object decreases exponentially over time toward the temperature of the surrounding medium. Now, it turns out that Newton's law of cooling also works for objects that are cooler than their surrounding temperature, that they will slowly increase until they reach that temperature of their surroundings. So the formula, we could say here, still works the same way. The temperature U of a heated object at a given time, T, time is T, can be modeled by this formula where capital T is going to be the constant temperature of the surrounding medium, U sub 0 is the initial temperature, and K is a negative constant. So a couple of these values we already know. We already know then that capital T is going to be 28 degrees because we were given that information in our problem, that the constant temperature of the room is 28 degrees Celsius. We also know the initial temperature. The initial temperature is given here. When it's first brought into the room is 10 degrees. So let's piece together what we do know about this model so far and see what we have left to find. So we have here 28 plus 10 minus 28 times e to the kt. Well, with a few of the parameters inputted, we see that these are okay. The one parameter that we need still is k. So this is where that second reading is going to come in and help us out. So for the second reading at time 2 minutes, we have an output temperature of 16 degrees. So let's use that fact. Plus, I'm going to go ahead and clean this up. That's okay. 10 minus 28 is negative 18. But I still don't know K. That's what I'm looking for. But I know that the temperature will be 16 degrees Celsius after 2 minutes. So this I can solve. This is an exponential equation. I can solve it for the unknown K by using inverses. So let's start by subtracting 28 from both sides. By subtracting 28 from both sides, we end up with the following. The next thing we would want to do is divide both sides by negative 18. And then after reducing that fraction, we get 2/3. And then this inverse is going to be changing the exponential form into its logarithmic form. And last but not least, divide both sides by 2. And we end up with K is the natural log of 2/3 divided by 2. Or if I want to do that as a decimal, I would just want to keep probably all of the decimal places that my calculator gives me. And if you just want to double check, this is what you should have. 25541 as what K is approximately equal to. So exact value if we need a lot of precision, and here approximate value if this is enough precision. And it turns out I think that's going to be enough in this problem. So our complete model for this problem, is U of t equals 28 minus 18e to the, and here's our value of k. We could either use that decimal form or the exact form, times t. So now that I have this model, I can put this model into any calculator, to Desmos, and whatever, it doesn't matter. But I'm going to replace t with 4. When I replace t with 4, I get an output of 20. And then when I replace t here with 9, I get an output of 25.10. So probably the most difficult part, if you want to even call it that, is getting this constant k through this formula for Newton's law of cooling, and then rewriting that form or formula for that model for your particular problem, and then you can get inputs and outputs as requested.